Okay, hello everyone. So we have been discussing about the different classification the caches can have based on how we basically fetch data in cache, then how we replace data, how we try to find the data or the block which we are looking for. Based on all these things, we have looked into different classification of caches. We have also seen basically the right strategy in the cache and all these things. Now we will be going forward and looking into or evaluating the efficiency of cache. So how do we figure out like how good our cache is performing? So let me jump onto that. So basically now we will be talking about performance, cache performance. Okay. So what is cache performance? So if we want to understand the cache performance, it's nothing but how much basically what is the average memory access time. So whenever my processor wants to access some data, what will be the average memory access time? So we are interested in knowing average memory access time. All right. So just to recall, we have our processor and the main memory. Okay, and in between we have our cache. Now processor will try to get the data from cache, and then the cache, depending on whether the data is available, it will respond. If the data is not available, the cache will try to get the data from memory. All right. So in case of there is a hit, the processor gets the data from cache itself. So when there is a hit, and if there is a miss, then the data, basically the request goes to cache. The cache then figures out that the data is not available, so sends the request to the main memory, and the data comes from main memory, and then through cache, the response or the data goes to the processor. So this is in case of miss. All right. So if we just try to understand this little more, and we try to draw a pipeline which indicates how the cache access actually happens in a program, and how it impacts the performance. So let's say we have a snippet of code which looks like this. So we have a, let's say, load instruction followed by some add, followed by another load, then there is a few more other instructions. So let's say add, branch, then subtract, and so on. Now the instructions will be fetched. If I draw the pipeline: fetch, decode, execute, memory, and write back. So let's say there was a hit, so there is no problem in executing this instruction, because whatever you are trying to load was there in cache, and you could load it very easily without wasting any time. So the next instruction also goes fine. So execute you can denote by E or X. So let me just denote by E in this case. Okay, so I might be running out of space. So anyways, so let's say this load, I fetch, then decode, and then execute. So in the memory stage, we will be loading the data, we will be reading actually the memory. Now if there is a miss, there is a cache miss, then you will be stuck in the memory stage till the data is available in memory. Okay, so you will be stalled, the performance or the work will get stalled, and whatever number of cycles it requires to get the data from main memory, for that many cycles you will be this task will be stalled, and that will impact your performance. So basically, let us say this is a stall, okay, and that will increase your CPI and all these things, and subsequent instruction will also get affected because you will be stalled because you will not be able to move. So you will be stalled in execute state for the subsequent instruction, then the next instruction will be basically stalled in the decode stage itself, right. So it will be stalled in decode stage, and the subsequent instruction will be stalled in the fetch stage. So because of this, you will have your performance degraded if the data is not available in your cache. Now, how do you calculate this average memory access time? So average memory access time, because you will have multiple memory access, right, and over period of your instruction, like you will have many such memory access. So you would be interested in finding out the average memory access time, because one instantaneous memory access may not be a good representative about how good or how bad your memory access is. So to find out average memory access time, so we are trying to find out the average memory access time. So now let us see what happens when the processor tries to access a memory. So processor puts a request to the cache, okay. Now irrespective of whether it's a hit or miss, the request goes to cache. So and that to evaluate whether there is a hit or miss, there is a fixed time, and that time is called hit time. So basically, if the data is available, then you immediately can send the data. If the data is not available, then you have additionally this penalty, miss penalty. So basically, for all accesses, there will be a constant time. That time is almost basically related to getting the feedback from cache whether the data is available or not. So this is called hit time. All right. Irrespective of whether it's a hit or miss, you will have to spend this time for every memory access. Now then, for some of the memories which some of the memory access requests which are which encounter a miss, they will have a larger delay, and which is called miss penalty. So the average memory access time for any memory access request is basically hit time plus what is the miss rate. So basically, if you have 100 requests, then out of 100, how many requests are miss? So let us say 10% of the request misses in general. So basically, this will be 10 divided by 100 multiplied by miss penalty. And that will give you your average memory access time. All right. So this is important to calculate how well your cache works. So what we have understood, we need a fixed amount of time to check the data whether it's available in cache or not. If the data is available, then you don't have to consider anything else, because for 90% of the cases this will be the situation. For in our example, we said that there is a miss rate of 10%, and for those 10% there will be an additional delay, which is basically the miss penalty. So whenever the data is not available in cache, you have to get it from the main memory, and that requires additional cycles, which happens, which is indicated here by stall, and that overhead you have to incorporate here. So, your average memory latency turns out to be like this. All right. Now, if cache was not there, then for all the memory accesses, like you, this miss penalty, proportional to miss penalty amount of time you would have spent. Now, this time is much smaller compared to the basically getting the data from main memory, because this hit time is pretty small, and then the miss, since miss rate is very low, let us say 10% or even less, then only 10% of the miss penalty actually contributes to your memory access time. All right. So, I hope this makes sense. Okay. Now, so going forward, we will be talking about the different categories of misses, or categorizing the misses, and it is very important concept. You will be asked many times in interviews, etc., about these categories. So, that is why these are important aspects of memory. Categorizing misses, and these are famously called as the 3 C's. Okay. What are the 3 C's? So, the 3 C's are basically compulsory, capacity, and conflict. So, let us go one by one. Compulsory. So, basically so this, as the name suggests, it's a miss which you can't avoid. Okay. So, when this kind of miss happens, because let us say you have never accessed a particular block, and then the request for that block comes in, then obviously there will be a cache miss, because the block was never accessed. There was no let us say no other block which was in the vicinity which got accessed, and all these things. So, basically there was no chance of getting the block because of let us say spatial spatial correlation and all these things. So, then the first reference to a block will be a miss, and it is irrespective of the size of the cache. So, this kind of miss is called compulsory miss. So, what it is? It is the first reference to a block. So, first reference to a block results in a compulsory miss, and this will occur even if you have infinite cache. All right. I hope this makes sense. So, as the name suggests, it is a compulsory miss, first reference to a block, and occurs even for infinite cache. The next one we will be talking about is called capacity miss. Now, these names are very intuitive. So, capacity, as it says that let us say I have a program, let us say my data size is 2 KB, but I have a cache which is of 1 KB. Then of course, I will not be able to basically have all my data which I need for the program in one go in my cache. So, basically my cache is small to hold all the data that I need for the program, and this kind of in those situations there will be a miss, because every time you request for a data which is not there in the cache, there will be a miss, because you can't put all the data which you need in the cache, because you have limited amount of cache. And it is irrespective of the replacement policy you have, because even if you have a very perfect replacement policy, your references to the data from the program will lead to miss, because you will not be able to put whatever all the things which you need in the cache. Okay. So, basically capacity miss occurs because cache is too small to hold all data needed by program. So, this can occur even if you have a perfect replacement policy. Okay. So, I hope this also this is clear. Now, the last one is called conflict miss. So, these are the 3 C's. So, compulsory, capacity and conflict. Okay. So, again here as the name suggests, I can just show you this diagram. I think this will make it much easier. So, we are talking about conflict miss. So, let us say I have in the previous example, as we discussed, like I have this 2-way set associative cache. Now, as we understand, like in 2-way set associative cache, in one set there we can put two blocks. So, let us say I need to work with block number 12, block number 4. So, I can put them here. But now, if block number 20 is also required, then since all these things are supposed to come in set 0, we will not have space to put block number 20. So, in that case, if the processor request for data from block number 20, that will result in a conflict miss, because this is creating a conflict. So, I can bring in block number 20, and now I have to evict either 4 or 12. Let us say I evict 12 and bring in 20. Now, in the next moment or next few after few cycles, you need the data from block number 12 again. So, then again there will be a miss, because now your set 0 contains block number 20 and block number 4. So, if you need data from block number 12, there will be a miss, and that miss is called conflict miss. So, misses that occur because of collision due to less than full associativity. So, if it was fully associative, then I could have. So, let us say I need to work with, or the processor, the program which is running, it works with block number 4, block number 20 and block number 12 simultaneously. So, if I had a fully associative cache, I could have brought in all the 3 blocks, and there would not have been any problem like conflict miss. But since I am using 2-way set associative cache, I have only two locations where I can put 2 blocks out of these 3, and that will result in conflict miss. I hope this makes sense. So, conflict miss is basically misses that occur because of collisions less than fully associative, less than full associativity. Okay. So these are the 3 C's of misses: compulsory, conflict, and capacity misses. So these are very important concepts. So please make sure that you understand them and you remember that what is compulsory miss, what is capacity miss, and what is conflict miss. These are not difficult concepts. These are very straightforward things, and I am sure you guys will not have any difficulty in understanding them. All right. So now going forward, we will be so as we have seen that our average memory access time. So remember that our objective is to reduce this average memory access time, right? So we want to minimize this average memory access time. So average memory access time has 2 components, this hit time and miss rate and miss penalty. So if we can reduce any of these components, then we will be able to reduce our memory access time. So now let's start with this hit time. So how hit time changes with the different things. For example, we know that the smaller the cache, the faster it is. So from these we can basically plot some results. So the objective is to reduce hit time. So we are trying to reduce hit time, and if we plot the access time for caches of different size. So we have 16 KB, starting from 16 KB to 1 MB cache, and then the caches are of like 1-way, that is direct map, 2-way set associative, 4-way and 8-way set associative caches. So if we observe the access time for these different caches, so these are experimentally acquired results. So you see that a small cache with very simple let us say direct mapping has the least amount of access time, and as you go on making your cache bigger and bigger, the access time goes higher and higher. But still, any size you take, the direct map has the lowest access time. Then as you keep on increasing the associativity, the access time almost remains in the same ballpark, and sometimes its access time increases a bit. All right. So you see that the associativity, with increased associativity, the access time increases, because your tag matching etc. will take more time. So if we want to have very good hit time, or if we want to reduce the hit time, then from this observation or this plot, it can be concluded that a small and simple cache, so small in size as well as it's a direct map cache, will be giving you the best performance. Okay. So I hope this makes sense. Now the next thing we would be looking at, so feel free to ask me any question if you have regarding this. The next thing we will be looking at into, remember that the average memory access time is basically hit time plus miss rate multiplied by miss penalty. So we have looked into hit time, so we have also got some intuitive idea about how hit time can be made small and small. So we have to build very small caches with direct mapping, then the hit time will be really small. But there are again like everything else, there is a trade off. Like if you make your cache too small, then most of the time the data will not be available in your cache. So even though you have a very small hit time, but most of the time you will not get the data which you are looking at. So, your miss rate will go high, and that will not help in your performance or average memory access time. Okay. So, now let us look at how can we reduce the miss rate. Okay. So, one thing we can look at is the block size. So, we know that every time there is something we need to bring in from the main memory, we bring it as a whole block. Now, what should be the size of the block? Should we be a small one or a big one? We have motivated ourselves that for spatial locality, for exploiting spatial locality, we have to have block sizes which are not too small, because we know that if some data is getting accessed, there is very likely that the data around that particular block or around that particular byte which you are accessing will be accessed as well. So, the block size should play a role in figuring out what should be the miss penalty, in fact miss rate. So, basically if we have too small a block, then the miss rate will go high. Now, how about having a very large block? Every time there is a we need to bring in something from the cache, we bring it in a very large block. So, that can be one strategy, but if you have a very large block, if your data is not in that large block for some reason, let us say, then you will be wasting lot of your energy in bringing a large block and not getting the useful data which you are looking for. So, basically there is again a sweet spot, or there is some optimum size of blocks. Though the as you increase your block or decrease your block, the performance does not get drastically affected, but you do get some ideal block sizes. So, for example, 64 a block size looks like a more 64 byte or 64 bit block size looks like a more appropriate size, which gives you the lowest amount of miss rate. So, this is again a experimental result where miss rates are plotted on y axis, and on in the x axis the different size of blocks are experimented with. So, you see that if you have too small blocks, then the miss rate goes higher, which is very intuitive also, because we want to exploit the spatial locality. So, that gets affected if your block is too small. On the other hand, if your block is too large, then because you will be bringing in lot more data. So, if your data is not there in the large block, then you have to evict it, and that causes. So, basically that can create conflict misses, right, because you have already brought in a big data and the data is not the data you are looking for is not there. So, there will be a conflict miss, and so you have to bring in new data and all these things. So, but there are some advantages of also having large blocks. So, basically if you have large number of large size of blocks, the number of blocks will be less. So, the tag overhead will be much less. You can also exploit the fast burst transfer from DRAM. So, basically if your data access is of burst mode, so where infrequently, but at a very high rate you get data, then for a short duration, then it is called burst data transfer. It can also exploit the on-chip buses, which are big, so you can bring in huge amount of huge blocks at a time. But it can result in wastage of bandwidth if the data is not used, because if your application which you are running has a does not have very like say huge amount of data which are spatially correlated, then which are clustered, then it may result in wastage of bandwidth, and since you have fewer number of blocks, it will increase the conflict misses. Okay. So that's why you should to reduce miss rate, you have to figure out the most appropriate block size, so which is some moderate value. So 64 byte looks like a very standard block size for reducing miss rate. All right. Okay. So another so miss rate. Okay. So now if we want to reduce miss rate further, so one approach could be basically you use larger and larger caches. So this again from experimental results, this plots are created. So you see that if you plot miss rate per type of request, and if you plot the cache size, so basically here you have 4K, 8K, 16K and so on. So you will see that as your cache size becomes higher and higher, the miss rate goes down, and we have plotted it for different types of memory. So it's direct map, 2-way set associative, 4-way, 8-way, and these are the different types of memories and the types of misses. For example, how much is compulsory miss, how much is capacity miss, and all, so on. Okay. So you see that the miss rate in general goes down as you have bigger and bigger cache, which is again very intuitive. Now the thumb rule, again this is important, that this is not like something which is mathematically proven or something. It's from observation, empirical rule of thumb. It can be observed that if the cache size is double, so from let us say you go from 32 to 64, the miss rate, the amount of drop in miss rate is in the range of √2. Okay. So empirical thumb rule, if you double your cache size, your miss rate goes down by about √2. And other observation, depending on what kind of basically whether it's a 2-way set associative cache, 1-way set associative, 1-way or direct map cache, or 8-way set associative cache, etc., your performance also vary, cache rate, miss rate also varies. So how it is varying? So again, thumb rule, direct map cache of size n. So let's take this example. So direct map is this. So this is your direct map cache performance with size. So direct map cache of size n has about the same miss rate as a 2-way set associative cache of size n by 2. So let's take this example. So a direct map cache of size, let's say 64 KB, has a miss rate which is this, right. So a direct map cache of size 64 has a miss rate which is this, and now a two-way set associative cache, or a two-way set associative cache which has a size n by 2. So, let us say this is n. So, the direct map cache of size n has a miss rate of this. A two-way set associative cache of size n by 2 has a miss rate of this. So, you can see that these miss rates are almost same, right. So, the thumb rule says that, I will just write it down, direct map cache of size n has about the same miss rate as a two-way set associative cache of size n by 2. All right, and you can see this from here. For a direct map cache of size 64, KB has almost the same miss rate as a two-way set associative cache of n by 2 size, which is 32 KB. So, basically these are thumb rules, but these observations are valid. So, we can see that if we can increase the associativity, the miss rate goes down. If we appropriately choose our block size, our miss rate goes down, and for hit rate we have to select a small and fast memory. Now, obviously the question will be like how to reduce the miss penalty. So, whenever there is a even if we reduce the miss rate for certain requests, there will be miss, and at that time it has to be served. So, how do you reduce the miss penalty? So, basically you can look into the technology of how the memory access is going on, etc. So, there are many different ways, or many very interesting ways people have tried to optimize all these things, but we will not have time to go through them, and also this increases the complexity, etc. But one way to basically reduce this miss penalty, which is not very difficult to understand, I will try to just mention, is called victim cache. So, what is this strategy? So, we know that, so I will just very briefly mention this. So, the idea is very intuitive. So, you have your processor, then main memory, and cache. So, so what we have seen is that the processor requests and gets the data, and if the data is not available, cache requests to the main memory, and so on. Now, let us say there was a cache miss, and the cache now requests the data to be new data to be brought into the cache. Now, obviously you have to basically evict something to accommodate the new data. Now, the block which you are evicting, so typically what we have understood, that we will be evicting that block into the main memory. So, basically we will be if there is some update, we will be we will be sharing those update or updating that in the main memory, and then we will get rid of that evicted block. But we have seen that there is something called conflict miss. So, in the example we saw we discussed that if I have this this kind of a situation where, because I have a two-way set associative cache, but there are 3 blocks which are frequently used. So, because of this conflict miss, I will be going back and forth and have to get the data again and again, because I can store only 2 blocks at a time. So, to avoid this kind of situation where there is a possibility of this conflict miss, and then you might need the data again. So, instead of completely removing the data, the victim cache strategy says that you put a very small memory here and call it as victim cache, and it is a small fully associative. Cache for basically recently evicted cache lines. Okay. So, the idea is very simple. So, if your cache is, let us say 64 KB, then maybe you will only have few KBs, 1 KB or 2 KB of this victim cache. Okay. So, it can hold, let us say 4 to 16 blocks maximum. Now, the idea is that whenever the cache evicts something, you store it into the victim cache. Okay. Now, how it helps? So, every time there is a miss, so you first look at it into the victim cache. Okay. And if the data is available, then you get the data from here, and of course, you put the block also into the into your main L1. Okay. That way you can handle the conflict misses much better. So, this is one way to also reduce your miss penalty, because see, if there was no victim cache, then if the data was just recently evicted, but then also you have to get it from the main memory. But since you have now victim cache, though small in size, but still there is a good probability that whatever you have evicted recently, you might need that data, and you can get the data almost at the same latency as you would have got it from your L1 cache. So, that way with a small amount of additional memory, additional cache, you can improve your miss penalty significantly. So, this is one such idea, and there are many ideas which people use in advanced caches, but they require lot more other things to understand as well. For example, we have not talked about virtual memory, the concept of page, etc. So, we will to understand those things, we will have to learn about all those other things. So, we will not go into that at this point. I just wanted to show you one example of how you can handle or improve the miss penalty using some concepts like victim cache, and it's a very neat concept which helps you in storing the evicted recently evicted blocks in the victim cache for some time. And here you can use basically the concepts like how do you handle the handle if the victim cache is full. So basically you can use something like first in first out. So whatever block you put in first, that will be evicted first, and so on. Okay. So we will conclude our discussion at this point.